Well, we've certainly got some fun in store today, because this is the Annie by Fluxeon. This is a commercial induction annealer for cartridge brass, and a gentleman was exceptionally kind, sent this thing to me for free. Didn't have anything to do with the channel. He was actually frustrated with the company and their customer support and had sent this thing back. They sent it back to him anyway. Apparently it was such an ordeal, he was like, I'm just getting rid of it. So he offered it up for anybody that would pay shipping, and I jumped on that thing. So for the cost of shipping, I have a new commercial induction annealer. Although I say new, it's not new. I believe he even had it maybe secondhand. So the Fluxeon Annie, again, is a commercial induction annealer. You can see this one has some cooling set up on the back. I think there maybe was supposed to be a pump with this thing. I'm not sure. It's got a little coil here. This thing seems to be something like a 18.5 millimeter diameter to the center of the coil, so something like 17 millimeter internal diameter. Really nice connections compared to kind of the homebrew stuff that I've got. This is made fairly decent. He sent me a full kit, and so I even have a foot switch for this thing, so you can control it with a foot switch if you want. But what I'm most interested in is seeing what they got going on inside. So I'm gonna crack into this thing. Now right away on the back, they've got some stuff here for a transformer. It says it's a 9-to-3 transformer for 10 amp, 120 volts. So I don't know. Let's just get into it and see what's inside. So, by the way, the specs on this thing, it draws supposedly 10 amps from the wall. Haven't tested that yet, but that would put it in the 1,000 to 1,200 watt range. The frequency operation is supposed to be somewhere between 40 and 90,000 hertz, so 40 to 90 kilohertz. So that's pretty normal for cartridge induction annealing. All right, so inside the back panel, we just got some connections, cooling fan, it looks like. And here we've got our hookups for wall power. We got our ground over here. Nothing too strange there. So the case is all aluminum, just all extrusions. Let's see. All right, so first interesting thing, and I haven't gotten it all the way open yet, but let's see if I can zoom in here and show you. The gentleman did say that he was having some trouble with this thing, and come on, get in there and focus. And if you look right there, there's a yellow wire that's kind of frayed. And interestingly enough, it kind of seems like whenever they put this fan in, that it may have either smashed up against this, or maybe even the fan blades abraded that wire at the back. I'm not 100% sure. You know, there's no way to really know, but I do notice that the top portion of this fan, they've like broken some tabs out there. Because usually you'd have screws going all the way through. There'd be a plastic frame that it would mount it. So I don't know if you can tell in the video, but this plastic right there has been like trimmed off for this fan. And look, that could just be for space and other stuff. It's not like, you know, that plastic's doing anything, but I wonder if whenever this thing got shoved in, the packaging was so tight that it pinched a wire, or those fan blades abraded it. All right, we got our first look inside here. So the bottom panel, once you get the feet off and the back cover off, it slides out because there are channels internal to these aluminum extrusions. So slide that bottom panel out, and here is your internal. Really interesting stuff going on in there. I mean, look, here's your big internal transformer. I'm thinking that this is probably Litz wire that's, you know, being wrapped around that outside, probably some Captain tape wrapped around it for insulation. But maybe looks like an iron core, some sort maybe, or some sort of core there. I don't want to say iron because I don't really know, but definitely something going on there. We got a bank of caps. Looks like we got a little, probably small power supply for low voltage power and stuff. Controller circuitry needs power. So I can also see along the internal edges, I don't know if you can see way down there, And over there, I've got, it looks like MOSFETs or IGBTs. Maybe that could be actually bridge diodes over there. Yeah, those look like bridge diodes. And on this side, I think maybe they're MOSFETs or IGBTs. So interestingly enough, there's some anti-tamper mechanisms in here. They've bent these screws on the front mounting, and it was definitely intentional because they were both bent the same way, I'm pretty sure. And that makes this harder to get out. And that's the main connector here for this part. They were very long screws. They were bent down, and then they had like celastic on the end. I am going to go ahead and back those out. I'm going to try not to damage the case because that's actually the part that I'm worried about the most, would be damaging the aluminum. I could maybe try to cut them off with some bolt cutters. That would maybe make more sense because it's probably not hard to find these screws. I'm sure they're standard thread, but get these out and then we'll be pretty close to getting this thing unbuttoned. By the way, these things on the side are just filters. These aren't fans, as it turns out. I thought maybe there'd be fans inside. There's not. They're just little filter ports, so that's kind of interesting. I don't know why they would go through all that trouble whenever it seems like something simpler would work, but anyway. All right, well, we got into it. So basically the side panels just slide on, and then there's clips holding all the heat generating devices up against the aluminum extrusion. So you just kind of got to knock those out, and there'll be a trick to get back in. I assume you'll just have to put them in and then kind of tap them back over so that those spring clips hold your MOSFETs and stuff up against the heat sinks. So far, my first impressions just looking at this thing is, man, it's kind of weird what they've got going on. I see no fewer than 3 low voltage power supplies, maybe 4, depending on what you talk about. So this one in the middle looks to be a 12 volt output. Over here on the left, this looks to be another 12 volt output. And then down here on the bottom, there's another little transformer with another power supply, and that I think is 22 volts. So why you would need 3 separate power supplies, I am not really sure. The other weird thing is on the back fan, it has its own circuit board. And on that thing, there's looks like a voltage regulator and another like IC circuit, and it's got a button. Why on earth there'd be a button? Unless they just got a board that was kind of pre-made. I'm not sure. Like, either there's an explanation and I'm just not seeing it, or it looks really like an inefficient design where they just grabbed some parts that were already available or something. The front panel is connected with a 10-pin little ribbon cable here that goes down here. It looks like maybe there's a couple of relays potentially there. So I'm going to get in here and try to trace this stuff out and see what I can see with it. And I'll be back whenever I have my head wrapped around at least halfway what the heck they're doing. All right, well, let me give you my best interpretation of what the heck's going on in this circuit. So back here, this whole section is basically just your AC to DC conversion on the mains. And so basically you're coming in here with your line and your neutral. You're going through a common mode choke just to do some filtering. You got some filtering caps on here too. So next up, you've got some inrush protections. So you got a couple of temperature sensitive resistors there for inrush protection. You got a diode bridge rectifier, and you've got some bulk capacitors for energy storage, some film caps too. So all this is actually controlled by an SSR. So this chip right up here is actually a solid state relay that can be controlled by the main front control panel, and it can actually switch the power on and off to the induction system. That's basically how it's controlled. The induction system itself, you've got basically a big resonant tank. So you've got this inductor coming into this big transformer. This thing looks like the secondary, at least, has been hand wound. And so this is a center tapped primary. So DC basically comes out into a transformer in the middle of the coil. And so the primary has 2 leads that come out. one on each set of this bank of capacitors here. The secondary is connected to your work coil. So the outside of this thing says that it's a 9-turn primary, 3-turn secondary. And so you're going to get some step down conversion. So the voltage will be approximately 1/3 of the input voltage. And on rectified US house current, that's going to be like 160 to 170 volts. So that'll get split into 1/3. So you're going to be around 60-ish volts going through your work coil, but you will get 3 times as much current. Now, the important thing with induction heating is that you've got to have AC, right? You got to have some high frequency. This thing says it's going to run anywhere from like 50 to 90 kilohertz. So how does that happen? Well, that's where these capacitors come in. So these are going to form a capacitive tank that works with the induction of the coil here, and that's gonna form an LC oscillating system where the frequency is going to be dictated by the capacitance and the inductance. It's basically like a big spring, and whenever you hit that spring with some current, it's gonna oscillate at a natural frequency. Now, the important thing about that is to keep it going, you're going to kind of enhance the resonance with. Now, basically the way that works, like I said, this transformer is tapped at the center, and so DC comes in and it could go one of 2 routes, right? And what you're really trying to do is create oscillating current in this secondary. And so why doesn't current just go down one leg and then it's just DC going to ground? It's a direct short. Why doesn't that happen? Well, the ground is going to be controlled by these MOSFETs at the back. And so there's a pair for each side of this tank. And basically they're like switches. You turn one on, the current goes down that side. Then you turn those off, turn the others on, the current goes down the other side. And what that means is in this coil, you get current that will go one of 2 ways. Now, when you switch MOSFETs, you got to be careful because you don't just want to turn them off when there's a bunch of current running through it. That's bad. So the natural resonance of this system will create this AC signal. And what you want to do is time it so that you turn the MOSFETs on and off when that signal is right at 0. So the way that's controlled is down here at the bottom. So right here in the middle, you'll see this kind of longer chip, and that is a set of NAND gates. So those things can basically take signals and turn on or off based on the input conditions, and they're tied back with some feedback from the MOSFETs and everything else. And basically all you need to know is they will flip-flop. And so those NAND gates end up controlling on each side. Each pair of MOSFETs has its own little gate driver that drives both of these MOSFETs. In addition, you got a bunch of other kind of protective elements. So there's a bunch of diodes for over voltage protection. There's diodes on the gates for protection there. And there's a whole bunch of other stuff just to make it work better. But at the end of the day, that's basically what's happening is you are flip-flopping these MOSFETs on and off, and that will enhance the AC signal with the resonance, and you will get an AC signal in your work coil so that it will heat stuff up. So if you want to know more about this stuff and you're interested in looking it up, you can search online for what's called a Royer oscillator or a Baxandall oscillator. They're very, very similar, and there's some argument about what stuff should be called. And I'm sure somebody out there is really excited to correct my pronunciation. That is one of the internet's favorite pastimes, as I've learned. On the main PCB, it's not exactly an Arduino, but it is an Atmel 8-bit chip. This is a AT Mega 8-bit controller chip. You've got crystals. Again, you've got some low voltage stuff. So these kind of white chips that are sticking up, those are optocouplers. So basically just some isolated switching for a couple of accessories, I guess. You got a rotary encoder over here, and then you've got the kind of serial port out, which I guess this goes to foot control and anything else, because again, this has some accessories that you can put out. Again, you do have a, looks like a 5-volt regulator coming out and a big crystal oscillator there, but that's kind of it on the main board. One of the other things I would point out about this thing is there seems to be a few areas that were done by hand and some things that were kind of odd as far as the construction. So, you know, this main transformer, definitely this is not machine wound. You know, somebody did this. At least the secondary definitely looks manual. But on the PCB, if you notice on the bottom, it looks like it's been like broken or cut or trimmed to fit. I don't know what. I don't know that they didn't get the dimensions correct on something here, but this has been broken or trimmed. Now keep in mind, this is secondhand. I don't think it's been opened up before because, again, whenever I took it apart, it looked like, you know, nobody had taken the thing apart, but, you know, maybe the factory. So clearly there's been something trimmed or cut here. And so that's kind of weird. You know, I noticed the same thing on the fan shroud's been trimmed, so maybe there was like some interference here, I guess, and that was trimmed to fit manually, but that's interesting. The other thing is like some of the soldering was clearly done by hand, and I wouldn't call it the best. I mean, it's certainly functional, but there's some weird stuff here. I don't know if there was like a bodge or if they needed better power capacity on the PCB, but there's, you know, some wires that have been soldered in on a couple traces there. So again, whether or not there was a mistake or whether they just needed a little bit higher current capacity, I'm not sure. But I guess, you know, overall, I would say there's some of it that doesn't really inspire confidence as far as the quality. I'm not saying that's bad, because again, it's better than I can build something, but you know, for a commercial product, there's a couple things that are a little weird, just in my opinion. All right, well, I am finished and I got everything pretty much traced out, and so I will post up schematics as much as I've got done. I would, you know, not trust those completely. There are very, very likely errors because I did a somewhat hasty job going through all this, because once I got done with the main resonant tank circuit, I was much less motivated to go through the whole control board. So I did, but I also didn't triple check everything and verify everything. I didn't tag all the pins. I kind of labeled everything. So again, forgive me for not being as thorough as I might have been. I just frankly got demotivated with all this. I do have to say, one thing I was wrong about. The backside fan is actually connected. There are traces that go all the way from the back, and it does connect to the board, but it looks like only power. And so I don't see where the main board is controlling the fan. It looks like it's just turning the power on and off, which means the thermal control still appears to be totally negotiated by that PCB back here on the fan, which is, I don't know, like I said, a little strange. I want to put this thing back together, see how it works. I did fix this wire at the back that had been abraded, so that should resolve any problem that was causing. Although it didn't look broken, it just looked a little frayed on the side with the insulation. So let me get this thing back together and we'll give it a demo. All right, well, this is going to be a bit redneck, but I'm going to measure the frequency response on this thing, and I'm just going to use my oscilloscope, and I've got a little coil of wire here, and so I don't really care about measuring voltage or anything specific. I just want to know frequency, and so this should pick up any EMF that this thing kicks out. And you may or may not be able to see this line fuzz up a little, even just the probably power supply noise coming through this thing. So let's give it a run and we will see what we pick up here. All right, so we're going, and let's give it a shot. So there's the waveform. It is more or less a sine wave, so that's good. Let's see. So I've got a frequency down here. I don't know if you can see that, but it says 66.666 kilohertz. So right about what they advertise for this thing. I think it's supposed to be somewhere around 75. This measurement may or may not be super precise the way I'm doing it. You know, I don't have anything in the work coil, and that can change the frequency, but it's certainly in the range they advertise. I've done this a couple times, and I've been getting a result somewhere in the 65 to 75 kilohertz range for this thing. So it does seem to all be kind of working the way they say. I'll also say, as far as the coil, This is maybe one of the quality pinch points. Whenever they wound this coil, it does seem to have a bit of a flat spot in the bend down here, so you won't get great water flow through this coil that they got. It does seem like they used very small tubing on this, and again, there's good things and bad things about that. The good thing is you get your inductance with a really small coil. The bad part is you don't get good water cooling, and that coil being small, not having a lot of mass, it's going to get real hot real quick. Now, let me show you a little bit about the way this thing operates. It's very simple. You've got a breaker right here. You flip that, it comes on. So here's your knob to adjust your settings, and it's basically push, and now you can adjust your timing. It goes from 0 up to 20 seconds, and it does rollover, so that's nice. I can't imagine anybody needing 20 seconds out of this thing. I've been running it at less than a half a second just to do measurements. You've got a start button. I've also got the foot switch here, so that just plugs in a little 3.5 millimeter RCA jack. So this accessory port can be used to run other things like the water pump for this thing. It can also be used, I believe, to trigger a drop gate. So you could integrate this thing pretty easy into an automated system, I feel, where you're doing some sort of drop and then this thing is triggering the drop gate that cycles the feed or something. I'm sure that all that could be wired in here pretty good. Now, all this, I guess we should verify that this thing will heat up some brass. So I've got a old whipped 6.5 Creedmoor here. Let's set this thing to, just do 1 second, see where 1 second gets us. Definitely heated it. I didn't see it glow. I would be testing with Tempolac, but I went to get my Tempolac and all the solvent has evaporated, so it's a brick right now. Let's go up to, so one error here seems to be on the rotary encoder, has some problems at some settings, so I can't do it at 1.5 seconds. Let's do 1.6. So here's 1.6 seconds. I mean, it's definitely getting there. So let's try a piece of 223 brass. I've got this thing set still to 1.6 seconds. Let me see if I can see this thing glow at all. Not quite at 1.6, so let's go up to 2.6, I guess. Oh yeah. So a couple of seconds, looks like, for 223 brass. It's where you got to be careful on your coil. The coil is already kind of smoking a little bit. So I'm going to stop there because, like I said, without water cooling, you don't want to run this thing very much. So, you know, it does look like 2.5 seconds for a piece 223 brass, which is pretty darn good. I would say that this thing is likely on par, at least, with my big 1,000 watt induction annealer that I built. They function differently, at least in how they generate the alternating current for the coil. Mine uses a different type of ZVS system, but similar power levels. This thing's supposed to be rated for like a 1,200 watt output. Mine's running 1,000 watts, and kind of similar on the time scale here. You know, again, I don't want to say whether or not mine's better because I haven't really done a lot of thorough testing, but certainly this thing will heat up your brass and it'll get it there pretty darn quick. That's, I think, where I'm going to stop this one. I mostly wanted to look at the circuit, and now that I've kind of looked at this thing, I think they've done some smart things and some things that I have questions about. I think their induction circuit is pretty smart, what they're doing, because it does step down the voltage on this coil. So this coil should be running under 75 volts, which is getting down there close to low voltage range, where it's not super dangerous to have this thing as far as the voltage that's coming out. Does run a lot of current. They do have water cooling ports on this, so it is kind of ready to be used in a more heavier duty environment. The downsides of what I've seen, and I just noticed I forgot one screw on this, so I need to get that put back in. So as far as the things that I don't like about it, I don't understand some of the stuff they've done on the low voltage side. You know, I know that there's some isolation, and they do keep kind of some of the power supply separate on your accessories from your main board, and I get maybe you want some isolation there, but you know, using the pre-built low voltage power supplies adds some cost to this thing. The thermal management, I don't understand at all why that's not being controlled by the main controller. And again, maybe I'm just wrong. Maybe I just don't understand what they're doing there. I've seen a couple of build quality issues where some of the soldering looks like it's clearly been done by hand and not extremely well. You know, that frayed wire at the back, again, maybe somebody took this thing apart, so I am trying to be careful about blaming Fluxeon for that, but I mean, that PCB looked like it had been hacked on, the fan shroud looked like it had been hacked on. There was like handwork on this thing that just doesn't make sense on a commercial piece of equipment. And so overall, like it's kind of good and bad. I don't know, you know, I want to stop short of saying whether or not I would recommend this thing. I think for the price, it certainly does the job. And I have no doubt about the electrical capability of the Induction itself. I think most of my concerns are a little bit more on the low voltage side and some of the choices they made, and a little bit of the build quality seems a bit lower. So anyway, that is a little look at the Fluxeon Annie induction heater. So if you got any questions, comments, or feedback, as always, feel free to leave them down below. I will post up the schematics that I put together for this thing. Again, be careful using them. I do expect them to have errors, but I'll put it out there for you on a GitHub. Anyway, that's it for me. Thanks for watching.